Hello everyone, my name is Sam Saidi and I'm today's reporter for Experiment 3 Rank and Cycle Experiment. In today's presentation I'm going to go over the introduction, objective, equations, theory, data reduction, calculations, results, conclusion. Then I'm going to show the references that I used to achieve today's presentation. Rank and cycle is used in most power plants, steam turbines, fuel, regeneration, and reheat machines. So the efficiency of the Rankine cycle is based on heat loss, pressure drops, and also other factors. There are two main objectives of the Rankine cycle experiment. The first objective is to understand the operation of the Rankine cycle. The second objective is to measure relevant data and to calculate the most important parameters that is associated with the Rankine cycle operation. For instance, both work of the turbine work and the turbine and pump, plus both the heat of the condenser and boiler. Here are the equations that I used to calculate and to reach to my final results. Basically, for the pump work, I used minus specific volume multiplied by the difference in pressure. And for the thermal efficiency, Qin minus Q out over Qin. Basically, Qin or heat in is the heat from the boiler, and heat out is from the condenser. And here we can see that the heat in is H1 minus H4, which is enthalpy, H1 minus H4, and all of those values are obtained using the steam tables, and I'm going to show how I figure out the values in a bit. Here's like the theory of the Rankine cycle. It's split into four processes. From one, the water that is condensed, that is out from the condenser, enters the pump, and the pump pressurizes the water and sends it to the boiler. The boiler heats the liquid, and it switches to what I call superheated state. Then it goes in the turbine, which is a steam, and the turbine, what it does, the turbine produces work from the steam that is out of the boiler. Then the steam goes to what I call the condenser, and the condenser condenses the steam into liquid and goes back, and the process keeps on repeating. And here's the ideal, the PV and TS diagrams. I had to plot approximately maybe like 9 diagrams to figure out the values. So those are the data reduction, for instance, turbine exit pressure versus time, and other. So by plotting those diagrams, I had to figure out how to mark the steady state. From the steady state, I used the values. So those values were the values that I got from the steady state were the values that I used for the calculations. So basically, for the turbine inlet pressure, I got 16 psi-G. I had to convert this to kilopascals because the steam tables are based on kilopascals and other to make the calculations easier. I had to add plus 14.7. 14.7 is the absolute pressure at sea level. And then I obtained, so I had two readings because I had to compare those two values. So the turbine inlet pressure and the condenser. And here, as we can see, I had to have obtain the values of the enthalpy, entropy, and specific volume to do the calculations. The results for the pump work I got a minus 0.786. And for the boiler heat N, I got 1,756.874. The condenser heat, I got minus 2,181.59. For the thermal efficiency here, it was like, I think, an error here because I had a really small value for the thermal efficiency. It should be bigger than this value, but I think I switched the condenser and the boiler. Something happened wrong. But I reached a really far level of calculation, so I couldn't go back and redo the calculation. But I think something went wrong in the thermal efficiency, because the thermal efficiency, as I mentioned previously, is Q in minus Q out over Q in. And just to conclude, there might be possible sources of error. It might be, those error might be because of human error during experiment, calculations error, heat loss, pressure drops, or other factors. Are there any questions?